First things first, IoT, or Internet of Things, describes a network of connected, interrelated devices that exchange data with one another, as well as with the internet. They can be sensors, actuators, or any combination of the two. IoT is a relatively old technology from the 1990s, but it really hit the mainstream recently due to a series of advancements in manufacturing, networking, and now AI. Respectively, these mean cheaper, more efficient, and more powerful devices, increased connectivity and so increased range, and finally, AI allows a more effective utilization of the massive amounts of data that the sensors produce. So, because of these, there's been a massive increase in usage of IoT in industry, with the largest two adopters being the automotive and manufacturing industries. Manufacturing is probably pretty far removed from the average person's life, but you've probably noticed that in cars you get heated seats and GPS and so on. That's IoT. We'll come back to these later, but now let's talk about some technical restrictions that IoT faces. Most of the issues come from IoT's biggest strength, its connected nature. The more devices in an IoT network, the more complex and powerful it becomes, and the more points of failure there are. A network is only secure as its weakest component, and IoT devices have a pretty big weakness holding them back: battery power. It means they have limited power, the rate of consumption of which affects their operational lifespan. While more complex security protocols offer, more security, more operations for encryption, decryption, and data verification means more power usage, means less lifespan. That means you have to charge, repair, or change the devices. That means it costs more, which sucks, and a lot of businesses and even people often prioritize money over security. Now, some have continuous power sources, but adding in another dependency for the system to work on isn't always the best idea for critical systems. But building on that, let's go on to the next point: reliability and the consequences of when an IoT system fails. IoT devices are dependent on several things that can potentially undercut their reliability. Firstly, as you might have guessed from the term IoT network, they're often reliant on a network between devices. That could be physical, wireless, or a cross between the two, but it adds another potential point of failure. However, it doesn't take a network outage to have communication problems, because although not a problem caused by IoT, interference and congestion is unfortunately very common on the 2.4 GHz radio broadband channel that most wireless IoT devices operate on. They keep working at this level, however, because moving up would be more expensive to produce, have less effective range, and crucially, consume more power. Staying at the level does have the cost of high latency or straight up inconsistent usability in more crowded contexts. Just to dump some more on the top, IoT doesn't have a global standard. That means that devices have to be configured and interfaced, and the systems controlling them have to be constantly updated as new ones are integrated or removed. And human error yet again adds in another potential point of failure. Of course, that's all well and good when the smart dog feeder bugs out and dumps half a month's worth of food for a very happy pet, but IoT systems go beyond trivial household appliances, and with industrial usage, the cost can often go beyond a bigger bill or inconvenience and have a human cost. Passing over the blatant example of two other large sectors that employ IoT, the healthcare and critical infrastructure sectors, I think a more telling example is in manufacturing. A sensor that checks the stress tolerance or fault level in tyres, let's say, I don't really know the car business too well, is unlikely to be a major security concern. But that sensor is a moving part. It experiences wear and tear, and its lifespan is a range, not some precise point at which they'll repair it. If this device malfunctions and the tolerance spikes just a tiny bit, just enough that 2-3 months down the line the tyre fails just a little bit too early, well, you can imagine. By the way, not only can that sensor have massive consequences for consumer safety, it's also taking the job of a worker who was probably replaced. IoT creates jobs, but it also makes an increasingly large number obsolete. But that's enough about what could go wrong with the system. Let's talk about what sucks when it goes right. For one, data. The businesses that run these services aren't really our friends, and data is a very useful and valuable commodity. The issue of IoT is it doesn't just monitor what we put out into the world as social media, website accesses, and form filling or whatever. It goes inside of people's homes, their cars, everywhere. And legislation is, as always, very slow to catch up. The EU only passed a law prohibiting companies running IoT services from selling the data they generate to unrelated third parties last year, and they didn't ban them from using it for whatever they want. To end on a very happy note, fines in the EU for violations of the general data protection regulations have gone up from €72 million in 2019 to just over 4 billion in the year so far. To conclude, even if the tone of this was a bit negative, IoT will definitely greatly change our society in one way or another. For all of its flaws, it allows us to have a much larger and easy degree of control over our homes, infrastructures and equipment in a way that was not achievable with the mechanical systems of the past. It has incredible but also easily abusable potential in monitoring, whether that be geological events and natural disasters, medical systems in emergency wards, or population surveillance by authoritarian regimes. Thank you very much for watching. So first we initialize TFT with a rotation of 1, meaning it's horizontal. Then we attempt to connect to the Wi-Fi using the SSD and password provided. If it succeeds, we connect to the Wi-Fi, and if it doesn't, well, we keep repeating until it successfully does. Then we configure the time based on the time region we're in. We're in Great Britain, whether or not we're in daylight saving zone, and the NTP server we're going to collect the time from. This is important for the next function, serial time. Serial time runs and defines a structure called the time. Then we add to the time the local time. This is the function that actually goes and collects the time data. If we're not successful in doing so, it will print that we didn't, and then it'll repeat. Otherwise, it will print all of this information to the screen, which will be shown now.